Hello, everyone. It's my great pleasure to welcome all of you to today's online seminar on interval methods in control engineering. And it's my very great pleasure to have Nacim Meslem with us today. And Nacim received his master degree from École Centrale de Nantes in 2004. Afterwards, he did his PhD in 2008 in Paris. And since 2012, he has been an associate professor at the university. Okay, now the mixture between French and English is starting at the University of Grenoble. And yeah, he's member at the moment of GIPSA Lab in Grenoble and INP Grenoble. And yes, Nacim, the floor will be yours to present your work on secure state estimation algorithms for discrete time linear systems.
Okay, so I can start.
Yes, please go ahead.
Okay. Thank you, Andreas, for this invitation. So the topic of my talk today is about the design of secure state estimation algorithm for discrete time system with using a set membership approach. Before starting, let me recall briefly the two main categories of bounded state estimation. We can find the category which is designed on the classical Leonberger observer, but we have just to extend the classical Leonberger observer to the case of sets by using some or the theory of positive system, and always we have to find some similarity transformation in order to preserve some ordering properties. And on the other hand, we can find set valued computation, which is based on a set extension of the classical prediction correction principle. And in this case, we have to apply step by step this prediction correction. Usually, we get a more precise estimation in the case of set valued method compared to interval observer. The main drawback for interval observer is the ordering property. Usually, finding some similarity transformation such that to preserve the positivity property of the dynamics of the estimation error doesn't match with the performance estimation. That means we can find the transformation that guarantee the positivity of the estimation error, but unfortunately, this similarity transformation doesn't allow us to get the best estimation in terms of the tightness of the estimated interval. So in this work or in this presentation, I want to discuss with you some new idea to design set-valued prediction correction estimator. In this approach, we propose to use the observability matrix in order to perform the correction stage. And in the same time, I propose to use a non-recursive formula in order to perform the prediction stage. And I want also to add some set membership test in order to be able to deal with some sensor faults and some malicious attacks on the sensors. So the plan of my presentation is divided mainly in 4 parts. In the first part, I state I present the considered program. That means the class of the system, the use assumption, and which is the objective to reach in this study. And then I introduce briefly the new set-valued prediction correction state estimator. I take some time to introduce the new prediction stage and then the new correction stage. And then I show how one can align the proposed set-valued state estimator with some consistency technique in order to be able to deal with the presence of sensor faults and malicious attack or cyber attacks. And then I combine the classical set-valued state estimator with these consistency techniques in order to get a secure set-valued state estimator. And then I finish my presentation with an illustrative example. So the case of considered system are discrete-time linear system described by difference inclusion. Why difference inclusion? Because here we assume that the dynamics of the system is subject to bounded state disturbances, here represented by intervals. So in this presentation, all parameter or variable between square bracket means intervals or boxes. And in the same time, we assume that we have several sensors that can measure different output of the systems. And in this case, these sensors are also subject to a bounded, unknown but bounded measurement noise described here by the VK box. And here the element or the parameter I represent the number of the used sensor. In this context, we consider only one sensors. That means for each output we have one value. But in general, we can consider groups of output of the systems. So under this boundedness assumption on the state disturbances, measurement noise, and the initial box of initial condition of the system with the observability condition on the pairs CI, that means for each output of the system, we consider or we assume that the system is observable, and we consider the case where the real measurement of the system are subject to fault or to malicious attacks. And these faults or malicious attacks are additive, considered additive to the real values of the output of the systems, and we describe it by AKI. And so the objective in this case is, and the objective in this case is to generate a guaranteed enclosure of the real state vector of the system that we have to estimate lower and an upper bound of the actual state vector of the system. And in the same time, we try to guarantee the resilience of these framing to the presence of faulty and attacks. That means even in the presence of these fault and attacks, the proposed set-valued state estimator has to conserve the framing property. So to do that, I said before, we will use a new open loop interval predictor. Why I say open loop interval predictor? Because in this phase, we don't need the measurements that we have. We use only the model of the system and its inputs in order to predict the future of the system. And to do this operation with a high precise accuracy, we will use a reachability method, which is based on an explicit expression of the general solution of a linear state equation, that we don't apply interval computation iteratively, but we have to apply this interval operation in a non-recursive way in order to avoid the wrapping and dependency phenomenon. And the second novelty is regarding the correction stage. Here, Compared to the classical approach, where the correction stage is done only by set inversion of the current measurement in order to get a new inverted state enclosure that include the actual state vector of the system. Here, we propose to use the observability matrix in order to inverse a sequence of the input of the systems. And then if we do that, we get an inverted enclosure of the state vector at the past time instant. And then we will find the best way in order to predict the corrected state enclosure at the past time to the current time instant. And in the same time, we have to equip this state estimator with some set membership consistency test in order to be able to detect sensor anomalies, that means faults and attacks. And in the same time, we have to distinguish between these anomalies. That means we will be able to say if the detected anomalies is fault or attacks. So I introduce now the prediction phase of the proposed set valued state estimator. As I said before, this prediction stage depends on the general solution of the state equation of the system. That means we don't use the dynamics which represent the system. That means the state equation, but we will use this solution of this state equation in order to be to compute a tight enclosure of the solution. So the expression of the general solution is done by, it's given by this formula, and so. And here we by XS we present the initial conditions. That means from a given initial condition XS, we are able to compute the future evolution of the system case xk if we know the input of the system and the disturbance or the state disturbance that act on the system. So to get an outer enclosure of the actual state vector of the system, we have just to apply interval computation to this general solution. For this study or in this presentation, I used interval computation, but we can also use other kind of set valued computation like Zonotop, ellipsoid, or something like this. And if we present the advantage of this interval extension with respect to the iterative computation, here, thanks to this interval extension, we can compute at each time instant directly an outer enclosure of the actual state vector of the system from the knowledge of the initial condition. So if we do that, we can avoid the wrapping effect. That means we don't have to introduce pessimist at each iteration. Now, in order to implement this expression in more formal or compact formula, I propose this new line. That means this formula is exactly the same line, but it's represented in a more compact way, which is more easy to implement on a calculator. And here we have just to say here the matrix N sigma K is a matrix designed like this, is just a concatenation or an horizontal concatenation of a multiplication of the matrix A multiplied by the matrix E, and so on. We get, or we construct the matrix B sigma K in the same way. And by P or capital P between square bracket, we present and vertical concatenation of the feasible domain of the state disturbances at each time instant. And we get in the same way a sequence of the input of the system gathered in a vertical vector or vertical matrix if the system is of or the dimension of the input of the system is bigger than 1. Okay, so just to present the advantage of using the explicit reachability method with respect to iterative computation, let me consider the case of rotation system. That means system defined like this is just an autonomous system where the state matrix is a rotation matrix. That means at each step the state of the system undergo a rotation. For example, in this example, we consider a rotation of P over 4. That means if we start rotating the initial condition of the system defined by this box, we get the result represented in blue in this figure. That means by definition, a rotation system doesn't modify the volume of the initial box. That this initial box at each iteration undergo a rotation of P over 4. But if we compute this exact reachable set by using iterative method, we get at each iteration, or we introduce at each iteration a pessimism, and the accumulation of this pessimism over the simulation period how to say the accumulation of this pessimism provide an outer enclosure of the actual solution of the system, but the volume of this enclosure become very big in some iteration, which provoke in few iteration the divergence of this algorithm. But if we do the same thing, or if we try to compute an outer approximation of the exact reachable set of the system by the explicit solution or the non-recursive set-valued computation approach, we get the dashed green boxes represented in this figure. And here we see clearly that thanks to this explicit computation, we can manage the wrapping effect. That means the weight of or the volume of these outer approximation is always lower than a given bounded. So this example illustrates clearly the advantage to work with explicit solution than the iterative approach. So now let me go. Okay. Now let me go to the correction stage, and in this correction stage, as I said before, we don't invert the current feasible domain of the measurement. Our idea here is to invert a sequence of the feasible domain of the output of the system. That means if we rewrite the output equation of the system for different time instant, we can get the set of this equation. And in this formula, we can see that we can compute the output of the system from the knowledge of the initial state condition or the initial condition or initial state of the system at the time instant sigma k. Here, by definition, sigma k is just k minus S. That means we go back to this time, for the past time instant, and then we can express at H, we can express sequence of the output of the system from the knowledge of the state vector at the time instant sigma k. And all the parameters that are here, that means the matrices here, for example, I represent the observability matrix. Later, I give you the expression of these four matrices, and the definition of these vectors used in these equation are defined here. That means here we have a sequence of an input of the system, and this sequence are concatenated in a vertical structure. That here between bracket and we give here the input of the system at the time instant sigma k, and the input of the system at the time instant sigma k plus 1, and so on. We construct in the same way the output of the system, and also the measurement noise, or the sequence of the measurement noise, and the sequence of the state disturbances. So if the system is observable, that I introduce quickly the definition of these four matrices used in this expression. And as I said, if the observability matrix of the system, or if the system is observable, we know that this matrix is invertible. And if this matrix is invertible, we can invert this equation in the sense we can compute the past state vector of the system from the knowledge of its sequence of output, input, and the state disturbances and measurement noise. So thanks to the observability of the system, we can reconstruct exactly the past state vector of the system. And to do that, we can generate this equation or extend this equation to the set-valued computation in order to get a guaranteed enclosure of the past state vector of the systems. And if we look at this formula, here we find two terms. The first term is just a point estimation of the actual state vector of the system at the past time instant, and this point estimate can be computed directly from this expression, and we can prove that this estimation is optimal in the sense least square method. And the red terms here represent the interval or the confidence interval of this point estimate, because we don't know exactly, we don't have the exact values of the measurement noise and the state disturbances, but we know their feasible domain. And so we can add these as a confidence interval. And this confidence interval is about 100%. That means we know that the actual state vector of the system is inside of this box. That means the inverted box at the past time instant. And the matrices capital CP and capital CI are defined like this. And here by square bracket P capital and square bracket Z capital represent the concatenation of the feasible domain of the state disturbances and measurement noise. And the index I here represent the considered sensors. That means we can invert or reconstruct the past state vector of the system by using any sensors of the system, because we assume that this system is observable from any sensors. So when we invert the sequence of the measurement in order to get an outer enclosure of the past for the state vector at the past time instant, we can correct the inverted state by doing the following intersection test. That means we discard all incompatible part between the predicted state enclosure and the inverted state enclosure. Recall that the predicted state enclosure is computed only from the knowledge of the model of the system model and the inputs of the system, and the predicted one is computed from an inversion of the collected measurement from sensors on fixed time windows with dimension s. Here, as the variable s stand for the size of the considered window of types. So when we correct the state enclosure at the past time instant, we can come to the future time instant, which is defined by k plus 1, by applying an interval predictor. That means this interval predictor is computed directly from the explicit reachability method. That means without using iterative computation, we can go directly from the past time instant sigma k to the current time instant k plus 1 by using this interval predictor. And so the proposed algorithm is decomposed or is structured in two phases. The first phase is just an predictor phase, because here in this case we don't have enough measurement in order to apply the prediction, the correction phase, because to apply the correction phase, we need to get n measurements in order to be able to apply the observability matrix in order to reconstruct the state vector at the past time instant. So from k equal 1 to k n minus 1, and here n represents the dimension of the system, we apply just the predictor in order to get a guaranteed enclosure of the state vector. And then from k bigger than n minus 1 to infinity, we can apply the prediction correction phase. So for each sensor, we invert or we compute a guaranteed inverted state enclosure at the past time instant. And then we intersect all these inverted set with the predicted set in order to get a tighter corrected state enclosure of the system. That means we discard or we eliminate all inconsistent part of the enclosure of the inverted enclosure of the state vector with the predicted enclosure of the state vector. And so we get the best estimation or the tighter estimation of the state vector. And when we correct this state enclosure at the past time instant, we can go to the current time instant, that means, or the future time instant k plus 1 by applying the direct predictor. That means by using directly the explicit reachability method. So now let me introduce briefly or present briefly the main property of this algorithm. So the framing property is guaranteed by constriction, that by using interval computation and the intersection test, we can prove easily that the actual state vector of the system is inside of the provided boxes or of the state vector. But we can also prove that the weight or the largest side of the estimated state enclosure defined by square bracket xk are always lower than a bond, which is depend on two terms. The first terms depend, it's proportional to the measurement noise or the visible domain of the measurement noise. And the second one, it depends also proportionally to the state disturbances. And that means, thanks to this expression, we can see that if there is no uncertainty in the system, that means the measurements are perfect, that means that measurements are exact, there is no measurement noise. And if there is no state disturbances, or if these noise are known exactly, we can reconstruct exactly the state vector of the system. And in this slide, I don't want to spend a lot of time in this slide, but here we give a sketch of the proof of this formula. That means we start from the correction, from the prediction, from the correction, the corrected state enclosure, and then we have just to replace these corrected state enclosure by its inverted or its equivalent inverted state enclosure, and then to apply directly interval rules in order to get this formula. So I don't spend a lot of time on this demonstration, but if you want later to discuss it, there is no problem. Now let me introduce the used consistency set membership test that allows one to check if there is some anomalies in the data generated by the used sensor, and in the same time this test allows us to distinguish between fault and attacks. So to start, let me introduce the first set membership test, which is applied on the measurement. That means in this test, we have to check if the measured values, that means the generated values of the output of the system from a given sensor I, it's inside the predicted enclosure of the output of the system. If this inclusion is true, then we can say that the used sensor is healthy, and we can use it later in order to estimate the state vector of the system. And if this inclusion is not true, that means this sensor is faulty, and then we can discard these sensors from the estimation process. So this first test allows us to detect the presence of fault, and in the same time to form the set of valid sensors that we will use later in order to estimate the state vector of the system, or to estimate an outer enclosure of the state vector of the system. Now, the second test is based on or is constructed on the inverted state enclosure of the system. That means in this case, we can select randomly a subset S equal from the set S. Recall here the set S is the set of valid sensor. That means the validated sensor from the output set membership test. And then from each sensor in this set, we compute an inverted enclosure of the state vector of the system at the past time instant. And then we have to check if there is some intersection between this inverted enclosure and the predicted enclosure. And so if there is no intersection, we can say that the sensor used in order to get this inverted enclosure is faulty. That means there is a malicious attack that inject some faulty data in the used sensor. And it's worth pointing out here that in this case, the first test, that means the output set membership test, doesn't detect the presence of this faulty data. But thanks to this new or the second set membership test, which is based on a comparison between the inverted state enclosure and the predicted state enclosure, we can detect if there is some malicious attack injected in the data provided by the sensors. And so all sensors that where the second test 2 is false are kept in the new set, which is denoted here by S to start. That means S to start is the set for all sensors where these intersection test generate a non-empty set. That means there is some consistency between the inverted state enclosure and the predicted state enclosure. And so we will done the correction stage with all inverted state enclosure that belongs into the set S to start. So here, just to remark that all attacks or the distinction between fault and attacks are these two tests. The first one allows us to say if the detected anomalies is a fault, and this one allows us to say that the detected anomalies is an attacks. And so we have to combine this test with the proposed set valued state estimator in order to get secure state estimation algorithm. The first phase of this algorithm is the same as that presented before, because in the first phase we don't use measurement. That means this phase is not impacted by fault or sensors, so we keep it the same. And then for the next or for the second phase, we have to complete the former version by these set membership test in order to be able to face the presence of fault and attacks. So for the first step here, we have just to construct the set S. That means the set that satisfies the output set membership test. That means here the set S is the set of sensors or valid sensors. That means sensors where the measured output are inside the predicted enclosure of output of the system. And here we select a randomly subset S start from S. And why we say here where we use a random manner to select a subset S start from S, just in order to defeat any malicious attacks. That means the attacker or the hacker doesn't know which exactly the sensor we will use in order to estimate the state vector of the system. That means we just have to add a prevention stage in our estimation procedure. So, as said before, from the valid sensor defined in the set S star, we compute inverted state enclosure at the past time instant of the system, and then we run out or we carry out the second set membership test in order to detect if there is some malicious attacks in the sensors. And then we have to construct the new sets S double start in order to run out or to perform the correction stage and to get a closure or a corrected enclosure at the past time instant. And so we can propagate these corrected state enclosure to the next time instant k plus y by applying the predicted interval algorithm. And so we get an outer enclosure of the actual state vector of the system. And for the next iteration, we have to test again if the valid of the available data are valid, and we have to construct first the set S, and then we select from the set S a subset S equal to prevent the attacks, and we have to check again in step 7 here if there is some attacks in this available data. And so at each iteration we have to apply set inversion operator, correction step, and then propagation step in order to get this outer approximation. So I finished presenting the proposed set valued state estimator, and let me here to introduce or to present some simulation results on numerical example. This example is defined by these matrices. And for this system, we consider that we have two outputs defined by the output matrix C1 and C2. And for these two matrices, the system is observable. That means we can carry out the inversion step by using the observability matrix constructed from this pair of matrices. And here we take the two sensors in order to estimate an outer enclosure of the state vector of the system. And later in the simulation, we consider that the initial condition of the system is given by this vector, and its input is defined by this formula. So in the same time, we consider that the initial box of the initial vector of the system is given by these sets. That means for each state variable of the system, it's inside one of these intervals. And in the same time, we consider that the state disturbances are inside this box. And for the simulation, we consider a randomly uniform state disturbances. And for the measurement noise, we consider these two boxes. That means for the first one, it's the noise which corresponds to the first sensors, and the second box correspond to the noise of the second sensors. That means even if we have the same bonds, but the evolution inside these two boxes are different from the first sensors to the second sensors. So for the first simulation results, we have considered the ideal case. That means there is no attacks or no faulty. The system is only subject to state disturbances and measurements noise. And in this condition, our algorithm generate these outer enclosure. That means in blue lines or blue curves, we get the outer estimation of the state vector, and the green lines represent the lower estimation of the state vector for each state variable, while the dashed red line represent the actual state vector of the system. And as shown in this figure here, we get the convergence in 3 iterations. That means after just 3 iterations, that means after getting sufficiently information or output of the system, we can apply the correction stage, and then we converge directly to lower bound. That means for all k bigger than 3, the size or the largest weight of the estimated boxes are lower than 1. Here I put 1 because I observed that graphically. But if we use the formula given in the proposition, we get 6 or 8. This is normal because in the formula we have really considered the worst case, and the approximation is very huge. Then I can go to the second simulation test, and in this simulation test we consider just faulty sensors. That means for each sensors we have a fault which appears between the time instant 79 and 88 for the first sensors, and for the second sensors we add a fault at time instant or the interval between 149 and 158, and we will see how our algorithm react to the presence of these faults. So here I present the simulation results, and we can see that the proposed set-valued state estimators is able to reconstruct an outer enclosure of the actual state vector of the system, and this set-valued estimator preserve the framing property of the system, but we observe that when a fault appears, the estimated enclosure undergo some inflation. This is normal because when we detect a fault, we discard one sensors and we continue the estimation by using only one sensors. Then it's normal to lose some precision of the computed state enclosure. And just to emphasize or to highlight the detection of this fault, here I plot the predicted state, the predicted outer enclosure of the system output, and we see that when the fault appears, the intersection or the inclusion test on the output of the system is not satisfied, and this detection allows us to say there is some fault on the system. Here in these two curves we have just made a zoom around the time instance or the intervals where the fault appears. That means over the sequence 79 and 88, and these for the first sensors or the fault of the first sensors, and we do the same for the second sensors, and we see that thanks to the output set membership test, we can detect these kind of anomaly. And if this test say us that this inclusion is not true, then we can say there is a fault in the system. Now, for the third simulation test, we consider a fault, and these faults are defined by small magnitude and appears in very quick intervals. That means these faults appears between 79 and 80, and this for the first sensors, and for the second sensors this fault appears between the time instant 149 and 150. And if we test the output set membership test, this fault doesn't appear. If I go directly to this test here, no, not this one, this one. So here in this one, if I plot the predicted output enclosure and I plot the measured or the data generated by the sensor, I see that this inclusion is satisfied. So my algorithm or the proposed algorithm doesn't detect the presence of these attacks by using the output set membership test. That means the output set membership test, it's not enough to detect the presence of this kind of attacks. But if we carry out the second set membership test, which is based on the inverted state enclosure and the predicted state enclosure, we can detect that at the time instance between 76 and 70 and 80, there is no consistency between the inverted state enclosure here presented by the magenta curve and the predicted state enclosure here presented by the blue and green curves. And so thanks to these test, we can detect the presence of an attack on the first sensors. And we can do the same conclusion regarding the attack on the second sensors. That means between the time instant 147 and 150, there is no intersection between the inverted state enclosure and the predicted state enclosure. And even in the presence of this attack, the proposed set-valued state estimator is able to generate a guaranteed enclosure of the state vector of the system. And we observe that when these attacks observed, the proposed set-valued state estimator generate an enclosure with a larger or smaller larger weight. That means we keep the framing of the actual state vector of the system, but with a large size. But we can ensure that the actual state vector of the system is always inside the estimated state enclosure. So to finish my presentation, I have some remarks. The first one is about the use of set membership computation. That means in the context of bounded error context, that means when we consider state estimation problem in bounded error context, we should to apply interval computation or in general set computation at the last time. That means we have to use our knowledge about the system and its solution, and we have to use the analytical or explicit solution, and we have to apply interval computation on these explicit expression rather than on iterative computation. Because even if we apply the best optimization method on an iterative scheme, the wrapping effect is strong to be manageable. So the idea is to use interval computation at the last time instant. And if we do that, we can avoid the wrapping effect. And the second remark is about to use consistency technique in order to detect and isolate sensors, because based on this consistency technique, we can get a reliable decision on the presence or not of sensor anomalies. So for future work or as perspective, I propose to ally or to compile this approach with a more advanced moving target defense strategy. In this work, we have just say at the moment we can select randomly the use sensor in order to defeat or to deceive the attacker strategy, but I think we can also use a more advanced moving target defense strategy in order to deceive always the attacker strategy. And also it's of great interest to be able to extend this work to the case of actuator of the system. That means in this work, we consider the case of attacks or faults on sensors and I think it's more challenging if we can extend this approach to the case of actuator anomalies. So I finished my presentation. If you have some question, do not hesitate to ask me.
So many thanks, Nacim, for your very interesting presentation. And I'm pretty sure there will be some questions. At least I've written down a few of them. Is there anyone in the audience? Eduardo.
Okay, thank you, Mr. Anders. Thank you, Mr. Meslem. Maybe I have two questions. The first question is about the monotonic properties of the interval observer. Is possible to lose this property when occurs a fault? Is possible? Or
it's possible to lose this property, in which case?
Monotonic property of the interval observer. Is possible to lose this condition when occurs a fault or no? The condition, the monotonic condition always.
Here in this work, we don't use we don't use the monotonity condition to design these set valued state estimator. Can I say one of the advantage of this method, we don't need to guarantee the cooperativity or the monotonicity of the estimation error. So if we don't do that, we have a lot of degrees of liberty in order to design the best state estimator. This is the first one. And the first response. The second one, in this case, we don't use an observer again. We have just to collect the measurement over a time window, and then we invert this knowledge of the output of the system via the observability matrix of the system, and we get an outer enclosure at the past time instant of the system. And then we correct this inverted state enclosure at the past time instant, and then we come back to the future, that means to the current time instant, by applying an interval predictor. And I said before, the predicted interval doesn't based on an iterative computation. That means we use directly the corrected state to get an outer enclosure of the state vector at the future. So in this approach, there is no need of the monotonicity property of the systems to apply this approach. In other words, we don't use the observer the observer design or interval observer design approach, but we use a set valued approach, which is based on the classical prediction correction method.
Okay, thank you. My second question is about the sensors. For example, in the example, did you listen me? Sorry, because maybe the connection is not good. Okay.
Uh,
In
The
your
second question is about
the sensors, the sensor,
the sensor. Yeah,
the fall detection for the sensors, because in your example, you have two sensors,
yeah,
yes, and with
yeah.
one interval observer, possible to detect the fall for each sensor, yes,
Yeah,
or
yeah. We can run our estimator with one sensors is if the system is observable from these sensors.
okay.
But here we propose to use several sensors for two reasons. The first one, to get several inverted state enclosure, and so we can merge all these available data to get the best estimated enclosure. That means we can eliminate all inconsistent part from all these sets, and so to get a tighter enclosure. This is the first reason. And the second one, if we use severance sensor, if one is faulty or is subject to attacks, we can continue the estimation with the remainder sensors.
Mhm. But what happens if the two sensors fall, if the two sensors fall at the same time? What about with the interval
Yeah,
observer? What is
yeah. Yeah, in this case, yeah, in this case, we can't run the correction stage, and we continue the estimation with only the predicted enclosure. Because here the correction stage use the data generated by the sensors, but the prediction stage doesn't need this information. So if at each time we detect that all the sensors are faulty or are subject to attacks, we can continue the estimation only with the predictor. And in this case, we get an enclosure of the state vector of the system, but we lose in terms of the precision. That means maybe this enclosure will be huge in some iteration or something like this. But if we observe at one time that our estimated enclosure become large and large and large, we understand that all the used sensors are faulty, and we have to do something in order to overcome this problem or to stop running the systems.
Okay, thank you.
No problem.
Okay, do we have any further question in the audience? Maybe let me add a quick question. What you are supposed at the moment is that you know perfectly your system matrices A and B. Did you try out what is happening with your approach if you cannot prevent, is this increase the inflation of the interval width by the reformulation by directly computing the matrix powers in cases where you have interval uncertainty in the matrix elements? Do you have any experience already how robust this will then be?
To be honest, this problem it's very hard to solve, because when we use the predicting stage, we have to compute the power of the matrix A, and if the matrix A is uncertain, that means defined by an interval matrix, we have how say it, the redundancy phenomena, or the recurrency phenomena. So I want to say we can implement this algorithm even if the matrix A is represented by an interval, but we can guarantee the convergence of the state estimator for a large simulation period. That means if we do the simulation on just a few iteration, and we get precise measurement in order to correct the predicted state enclosure, maybe the proposed state estimator can provide interesting results. But if the sensor is not precise and the correction stage doesn't bring sufficiently information in order to contract the predicted state enclosure, I don't know exactly how to
Yes, I think even the more challenging part.
We can applying it, but depend on the pessimism introduced by the interval matrix A.
Yeah, I think even the more challenging part is the thing whether the observability matrix still remains invertible.
Exactly. Even I am not sure how we can check the observability of the couple ACI with A as interval matrix. So there is this problem is challenging. Before to apply our the proposed method, I don't know how to check the observability of interval matrices.
Yes, you remember I just recently sent you one of the articles from my colleagues from Wuppertal, where they also discussed about observability of nonlinear systems. And yeah, that's definitely a very nice outlook on future work.
Okay. To be honest, I don't yet read this paper.
Yeah. Okay. Great. Then I think we had plenty of discussions after your very interesting presentation. And many thanks again, Nacim, for your inspiring talk.
No problem.
Yes, we'll continue our series of interval seminars on Friday in 2 weeks. And until then, I wish all of you a nice remaining week. Have a nice afternoon and see you soon in 2 weeks.
Thank you. Bye-bye.
Thank you. Bye.
Thank you very much.